All right, welcome everyone. Wel- Welcome everyone to the April Virtual Astronomy Software Talks. We have two speakers today, both coming from the Netherlands, which is nice. Our first speaker will be Devarshi Choudhury. He is currently a graduate student at UVA, University of Amsterdam, who just submitted his thesis. So let's congratulate him on that accomplishment. He's going to tell us about a package called X-PSI, open source package for neutron star X-ray pulse simulation and inference. So, Devarshi, you can go ahead and share. We have 20 minutes for your talk, and then we'll give you a sort of a 1 minute interruption. We'll take some questions. We'll go to the next talk. Then we'll have more general questions towards the end.
Okay, great. Let me just share my screen. All right, so are my slides visible?
Yes, they are.
Perfect. Okay, good morning, everyone. I'm Devarshi Choudhury. I'm a final year PhD student at the University of Amsterdam, and I'm one of the developers of the software package called X-PSI, which is a software for neutron star pulse profile modeling. To give a brief introduction to the overarching scientific goal, we are studying neutron stars and trying to figure out the interiors. So these are objects, as you know, that are the remnants of massive supernova explosions, provided they do not form black holes. So you're left with objects that are about as wide as a city, but packing in more mass than our sun, making them the densest directly observable objects in the universe. Now, neutron stars have a rather layered structure, which can roughly be divided into crustal layers and a core region. The crustal layers, they are pretty well understood from first principles and with observations supporting those. But for the core, you encounter supranuclear densities, so densities higher than an atomic nucleus. And in such extreme regimes, we do not fully understand what the neutron star is made of, how forces of nature interact, whether we still have nucleons, maybe in superfluid or superconducting states, or whether they dissociate into deconfined quarks or reassemble to form more exotic states like hyperons and so on. And this is one of the holy grails of neutron star astrophysics that we want to try and address. But how can we possibly study such tiny, tiny objects so incredibly far away? Well, lucky for us, the core composition dictates what's known as the equation of state of a neutron star, which is the relation between the pressure on the y-axis and the density on the x-axis. The pressure and density through stellar structure equations directly have one-to-one correspondence to the mass and radius of the neutron star. Now, the mass and radius, coupled with the spin of the neutron star, governs how the exterior spacetime is going to be curved. So if you have any kind of surface X-ray emission, that has to traverse this curved spacetime, and this information gets encoded in it. Now, NASA launched a space telescope called NICER, which stands for the Neutron Star Interior Composition Explorer, particularly to study these surface X-ray emissions from neutron stars. So here is a closer view of NICER, which is rotating about, pointing at pulsars and tracking them. And this is one of the few telescopes that you can actually film and repair. In fact, there was a recent repair mission to patch micrometeorite damage on NICER. So this is an X-ray timing telescope with very high sensitivity in the soft X-ray band and very high time and energy resolution. And these are designed to particularly observe rotation-powered millisecond pulsars. So these are pulsars that do not have an accretion disk. And all of these surface X-rays emanate due to charged particles being guided along open field lines and bombarding on the surface. Now, the idea behind getting mass and radius from these X-rays is sort of illustrated in this animation. So imagine, if you will, that we turn off all sorts of relativistic effects. There's no gravity and so on. And we take the neutron star with a hot spot on the surface, and it's rotating. So the spot goes in and out of view, resulting in a light curve, as shown on the left-hand side. But because of relativistic effects, GR and SR, the spot actually lingers on for a longer portion of the time, which sort of has this effect of squashing the pulse profile along the vertical axis. Add on top the Doppler effects, such as Doppler aberration and beaming, and it skews this pulse profile. So if you have high quality data tracking this sort of pulse evolution, then you have a model that can describe these sort of physical processes, you can combine the two to hopefully infer the mass and radii. And this process is what's termed as pulse profile modeling, and that's shown here in this diagram. So on top here, you have an example of a pulse profile data set, which is your X-ray counts, binned as a function of the rotational phase of the star on the x-axis and the energy of the incoming photon on the y-axis. So once you have the data, you need a model that describes how this the surface emission will arrive at us, given certain hotspot configurations. We have to account for the telescope properties, how it's actually processing this extra data. And then you can compare the two, use Bayesian inference and statistical sampling to get your model parameters of interest. And this is what X-PSI does. It stands for X-ray Pulse Simulation Inference. This is an open source software package, which is available on GitHub. Also, you can find the link on the VAST website. And we published a paper about this on the Journal of Open Source Software. The core functionality, the goal of X-PSI is that it provides you the physical modeling framework to do pulse profile modeling in terms of relativistic ray tracing, allowing to define these sort of surface and curved spacetime, and also handling various sort of instrument responses to how you to sort of compare with the data that you receive. We additionally provide built-in visualization and post-processing tools. So once you're done with your inference or even during modeling process, you can visualize what you're doing. And there are tons of post-processing tools to actually understand the samples you've obtained. The design of X-PSI is object-oriented programming based, making it highly modular and customizable for your specific use case. So you can inherit the properties and cater it to your needs. It's a fast multi-level code with Python and Cython in the mix for things for computations that take longer time to do those faster. We also provide comprehensive documentation for this whole package. The application package interface is available online. We encourage community contribution. There has been quite a significant contribution from the people who have been using X-PSI so far. And of course, the software is built on many other packages, both Python and non-Python. So for example, Cython is one of the main examples, and then Cython has other dependencies. We connect to external samplers. Here's the logo of UltraNest. And the whole pipeline is made to be parallelizable. So that's why we have MPI and OpenMPN there. Now, before I dive into the design and the functionality of X-PSI, let me briefly take a moment to describe how we handle our open source software management. To start with, we adhere to the GitHub community standards. So we have README pages, full documentation pages, the API documentation. We provide a code of conduct and guidelines for how you would contribute to this code. We have licensed our software and have issued templates and have raised templates for how you could raise like a GitHub issue. We still need to develop a template for pull requests. That's something that only the core developers have been using, so we don't have it yet, but something to do. Additionally, there is not only extensive documentation of the API, we have provided lots of tutorials that depend on what you want to do with the package. And there's even a landing page which will guide you to the relevant tutorial based on your needs. Also, anytime we have published a paper using X-PSI, we have made sure to provide a full reproduction package for these publications to enable open science. Some additional things that we do. We have a mandatory code review process before we merge anything into the main branch. So here you can see that one of the core developers has to approve a pull request so that we don't accidentally break our code. This is something that sort of safeguards it from mishaps. We also add a bunch of tests, so unit tests and continuous integration tests. So the concept behind unit tests is that you sort of write these small test programs, for example, using a package like PyTest or so on, to test out, let's say, small chunks of your code, like maybe a function or a class. And the idea is that of course, if you provide something that this function expects, it should return what you reasonably expect it to return. But more importantly, if you pass on some gibberish, it should correctly raise that, yeah, it doesn't know what to do with it. If it gives you an answer regardless, that's more worrying. And with continuous integration tests, these are part of the GitHub actions. So basically, anytime a pull request is merged onto the main branch, GitHub sort of installs X-PSI from scratch on their servers, runs all of the unit tests, runs a couple of other tests, builds the documentation, does some more checks. And this is sort of to and once all of these are passed, only then will it fully merge it into the main branch. And this is again another safety feature to prevent any kind of like large failure. And last but not least, we arrange sprint weeks. So right now, twice a year, we host sprint weeks to sort of address the larger issues that have been raised on GitHub, or sometimes do some code cleanup, discuss the future implementation, and so on. In fact, in May, so our Amsterdam group will head to Toulouse, where we have a French wing to enjoy some nice southern French weather and go on with our sprints. Okay, so moving on to the design for X-PSI, here is an object graph. So this is a high-level object graph for X-PSI that most users would have to deal with. And each box here essentially represents a class. So the fundamental class here is the likelihood class. And the direction of the arrows basically indicate the flow of inheritance. So the likelihood class inherits all the information from these other classes. So roughly on the left-hand side, we have all the modeling aspects. So you have, let's say, the star, which inherits space-time. It can have multiple photospheres, depending on what you're trying to model. The photospheres would have hot regions. You would describe hot regions. And on the other side, you have sort of the data side of things. So you have the signal, which is your data once it's convoluted through the instrument. Is there any background? Are you accounting for any interstellar attenuation? And you could, of course, have multiple instruments, multiple telescopes observing the same source. So you could have multiple signals. Again, this is object-oriented programming based. So the idea is that these are core classes. You can subclass these to your own specific needs and pass on the information. The likelihood object then actually explicitly calculates the likelihood for given data and model parameters, which is then passed on to, which then connects to a sampling interface to perform Bayesian inference. So that was kind of the tip of the iceberg. So this is the full object graph of X-PSI. So all of what you saw previously basically is confined to the black portions in this graph. So that's a Python level. And then we have the Cython level, which we don't really expect the users to interact with. These are things that we kind of expect to be relatively stable over time. And these are also things that we need to perform quickly. So this is where actual relativistic ray tracing is taking place. And this can take time if you do it with regular Python code. And that's why we have incorporated Cython for it. Of course, the downside of using Cython is that now you have two different languages. It's not very cleanly installable using like a paper conda system, so you have to separately compile it. So now we are also contemplating and are considering using JAX as an alternative, where we have the entire code base in JAX to check whether it can achieve similar speed boosts as Cython provided us. And also, it might open up the gateway to using GPUs in a straightforward manner. Now, moving on to the actual modeling processes, starting with relativistic ray tracing. The idea behind this is that you're essentially trying to propagate a photon from the surface to a distant observer. And to do this, you're trying to calculate psi, which is the deflection angle, for a given photon that's emitted at an angle alpha with respect to the surface normal. For this, ideally, you would want to want the exact numeric, exact metric for a rotating neutron star. But computing this is prohibitively expensive when you're talking in an inference context, when you're doing this repeatedly for many samples. So instead, we go for an approximation, where we simply consider a Schwarzschild spacetime and introduce rotationally introduced oblateness into it, as well as Doppler effects. And this does a remarkable job at approximating the exact solution. So here on the bottom panel, we're showing the fractional difference between different implementations. And this dotted line here indicates the difference between the exact solution and this oblate-Schwarzschild plus Doppler approximation. And the level of this difference is far below what our personal noise in our data would allow us to infer anyway. So it's not really of concern. We have cross-tested our ray tracing implementation with other neutron star ray tracing codes. This has been thoroughly tested for many different cases, many different compactnesses of neutron stars, different surface configurations, and so on. Not going to go into too much details, but we compare, let's say, the pulse profile itself, as well as the emergent spectra. And we try to notice what differences lie between the different codes, between our own resolution settings, our own code, and so on. Having established the robustness of the ray tracing pipeline in itself, we also, of course, to model neutron star, need to know where the surface emission is coming from, which we do not know a priori. So what we do is we opt for phenomenological models that sort of capture the complexities we expect from detailed pulsar emission mechanism simulations. We go for like a circle-based parameterization to make it tractable for sampling, and use it to sort of overlap them and use it to form these more complicated shapes with multiple temperature regions or masking elements to create rings and crescents and so on. And for each hotspot, essentially, the surface is discretized into a regularized grid of radiating cell meshes. And each cell mesh, we can then assign a certain number of rays that are being emanated from it. We can also consider black body emission to arise from these from the surface, or as we do for real nicer analyses, we consider a more realistic numerical atmosphere model accounting for the atmosphere composition and how it affects the intensity of the emergent emission depending on the energy, the surface gravity, emission angle, and so on. Okay, so with our data and model in hand, we can conduct statistical sampling, for which we use so far for all of the real data analyses, we've used the nested sampling software called Multinest. But now we've also incorporated Ultranest into the pipeline. We have been cross-testing it to also check the robustness of each of these sampling methods. And we are looking forward towards a simulation-based inference. To give a quick overview of the nested sampling principle, the idea essentially behind nested sampling is that you want to compute Bayesian model evidences. And this quantity, I see a question in chat. Is it for now or?
No, we'll address that after. Yeah, just keep.
Sure. Yeah, so for nested sampling, the concept is that you want to calculate Bayesian model evidences, which allows you to compare how good a given model is for the particular data. And you get the posterior probabilities as byproduct. So quite simply, let's say if this is your prior space, you draw a bunch of samples, you compute the likelihood for each, you find the point with the lowest likelihood, say L1, and then you sort of try to approximate an iso-likelihood contour and sample only from within this contour. And as you're doing this, the area confined within this contour then corresponds to Z, which is your Bayesian evidence. And you keep doing this iteratively until you obtain your posterior. Now, Multinest and Ultranest both are nested samplers. Multinest, in very brief, Multinest uses what's known as region sampling, where they use sort of what's called a multi-ellipsoidal decomposition algorithm to sort of approximate the iso-likelihood contour. While this is great at understanding multimodal features, and it can address curving degeneracies, it might miss out if there's too sharp of a curving degeneracy somewhere. Ultranest sort of improves on this concept, where within a iso-likelihood contour, it does sort of like a metropolis-like walk to find another point in the vicinity that has a higher likelihood than before. And in this manner, the idea is that if you have a point here, it might walk into these territories to then also identify that there's a curvature going on here. It has many different ways it does this. Step sampling is one of them. There are other implementations as well, and this is the one we've tried so far. Nested sampling is, however, a very computationally expensive process, given our model complexities and the nature of the data. We have been running our inference runs on Snellius for real data, which is the Dutch national supercomputer, but we've also tested on smaller clusters, Helios and CalMIP. But our production runs, they take anywhere between tens of thousands to hundreds of thousands, almost up to 1 million core hours for a single run. So we're sort of really hitting computational bottlenecks here, and given future increments in data sets, more observations from future telescopes, improvements in physical modeling, adding model complexities, we need to make things faster. For this, one of the avenues we're considering is simulation-based inference. This is something we are just trying out. And the fundamental idea behind this is, if you have a model that can generate simulations, you have your prior space, you use it to generate a ton of training data set, with which you train a neural network, particularly a neural density estimator, to understand the relation between all of data and model space. Once you do that, a neural density estimator network in particular maybe say like a normalizing flow, is incapable of deducing what the distributions look like. And for a given data set, it can then provide you a posterior. Normally, neural networks take as inputs flat 1D arrays, but our data is an image. It's essentially a grayscale 2D image. So we are using convolutional neural networks, which use sort of like a kernel system to go over your image and preserve spatially correlated information. We've only tested this so far on toy problems with fewer dimensions, and the speed we've obtained enormous speed boosts. However, we are yet to fully achieve the level of precision that nested samplers are providing, but this seems to be mostly related to our choice of CNNs. So this is something that we need to iron out, and this would be a major improvement to our work. Regardless, once you have your posterior samples, X-PSI provides you a range of post-processing tools and visualization tools. Starting with the fundamental tool, which is to generate cornel plots. So here I'm showing just a few model parameters, so mass, radius, and a term called compactness. But typically for our models, you have somewhere between 10 to 21 parameters. So with the cornel plots, you can plot the posterior samples from multiple runs. You perform full kernel density estimation for these to obtain your credible intervals. You can overplot your priors here, calculate the KL divergences between the distributions. Not something that's shown in this plot particularly, but a feature that we have. We also have routines to generate spectrum plots for the posterior samples, but not just a regular spectrum plot, but one where you can extract the contribution of your individual sort of surface radiating elements. So maybe if you have two spots, so you can have spot 1, spot 2 in these color bands, and this is like a background contribution. We also provide.
You should wrap up. Sorry to interrupt.
Okay, yeah, I'll be quick. So you have other tools like plotting tools to see the geometries. We provide tools to also check the model outcome of your pulse profiles with individual contribution from the spots, as well as sky maps that allow you to generate, account for all the relativistic effects and how you would actually observe the star. And we have also tools for posterior predictive checking, where we basically take a bunch of posterior samples, compare it with the data, obtain the residuals, and try to see whether these look like Poisson residuals. Of course, it can be a bit hard to see them by naked eye, so we also have tools to sort of help you understand if there truly is a feature that your model has missed out on explaining. Okay, to wrap up, I'll just quickly show our headline results that we've obtained through X-PSI. Here's a plot of mass versus radius, and the various curved lines here are the theoretical equation of state models. And you have the mass radius contours that we've obtained for 3 sources observed with NICER. When you combine these measurements along with gravitational wave measurements, as was done by Rutherford et al., he's in the audience here, I think, you can constrain the equation of state space to this narrow band and already start excluding various models. Also, as a byproduct, you end up with these nice animations of the surface emission geometries, the hotspots on the neutron star, which indicate that you do not simply have a centered dipolar magnetosphere, but something more complicated, maybe a off-centered dipolar quadrupolar structure. And with that, I'll thank you for your attention and leave you with these nice animations here. Thank you.
Wonderful. That was very nice. And congratulations again on submitting your thesis. We'll take one question which was dropped in here, and then we'll move on to the next talk. The one question that was dropped was, have you considered using Julia, the Julia programming language, which they say is Python with NumPy and JAX built in and can compile directly to GPUs. So that would be a big change, but you were talking about the limitations of Python. So
yeah, indeed. So Julia is definitely an option as well. One of the concerns that we have a bit with Julia, having talked to some of the Julia developers as well as JAX developers, is just the long-term support for Julia, given that it's mostly used by academic communities, whereas JAX is now sort of going to be the replacement for TensorFlow within Google, and so there'll be enormous industry support for this language. But indeed, Julia otherwise is perfectly an alternative for this. But yeah, might be worth looking into. This is something, again, if you would like to also contribute, you're most welcome to. Maybe something we can also look at in one of the sprint weeks, in the upcoming sprint weeks.
Great. We'll move on to the next talk, and then we'll have like 15-20 minutes at the end where we can just have more general discussion. We are happy to have next Matthieu Schaller from Lorentz Institute. So continuing our Netherlands contingent today, talking about Swift, SPH with interdependent fine-grained tasking. So we're happy to hear from you.
Yay! Can you hear me? Can you see everything?
Yeah, it looks great.
Excellent. Yeah, so I'm a staff member at the Leiden Observatory, also in the Netherlands, to complete your the Dutch day, I would say. And so I'm going to talk a bit about our software package called Swift, and maybe it's going to be a bit different from the usual. I'm going to talk a bit. I'm trying to do some promotion here for task-based parallelism, and how maybe this is an interesting concept that can be explored for other packages as well on your side. Okay, so maybe just a tiny bit of context, what I'm interested in, and then so on. So I do numerical cosmology. I'm interested in understanding how we go from the cosmic microwave background on the top left here to the present day map of the universe on the bottom right here from a galaxy survey. So essentially taking the universe from 380,000 years old to the universe now, which is 14 billion years old or so. And more specifically going from very small fluctuations that people can solve analytically via perturbation theory and so on, where everybody's in happy land, going to the bottom right, where it's immense fluctuations in the density field, where obviously we can't use classical methods from physics, and we have to resort to numerical simulation or numerical approximations. And so the questions I'm interested in are, are we going from the top left to the bottom right with lambda CDM, the vanilla cosmological model that's been around for 25 years now, or should we invoke some dark energy or modify laws of gravity? Or is dark matter maybe warm, or does it have some interaction rates and so on? Are there massive neutrinos and all of these prospects? And because I'm not smart enough to do this by hand in pen and paper, my job is I go in a supercomputer, I teach the computer how to solve these equations, and then the computer does all of the work for me while I debug it, mostly. But I would say while I'm on holiday would be the ideal setup. So that's what we do. And then the main package we have is Swift, which has been going around for a while. It's been using for different kind of applications, also being used a lot for planetary applications with planetary collisions and like moon formation scenarios and so on. You can find the link here to the archive, also to the software open source software library. And it's it's an endeavor with a large endeavor with a lot of people involved. And in a nutshell, what do we provide? So it's a large code base with more like 100,000 lines of code. It's all in C, and it's designed to run on very large machines as well as on laptops if needed. And so in terms of gravity, so we're solving short-range gravity using a fast multipole method. We can do long-range gravity using a particle mesh method. Our method of choice for hydrodynamics is smooth particle hydrodynamics because it's very adaptive. We'll come to that in a minute. Then we also have dedicated equation of states for planetary applications. So if you're interested in crashing planets, which are made of different materials, we can provide this. If you're more interested in large-scale structure cosmology simulation, then we can also compute on the fly light cones. If you're not familiar with this, it means we're placing an observer somewhere in the simulation, and then we're looking at with a look-back time, and it takes the time it takes for the photons to arrive in your telescope. This is included in the calculation to have a representative sample that can be directly compared to observations. We can also solve for neutrinos. We can do self-insuring dark matter. We can do a bit of radiative transfer. And then we also have, which maybe is a bit different from many other packages, we actually provide full subgrid models from certain simulations. What we mean by subgrid models here are models of galaxy formation. So, formation of stars, formation of black holes, the evolution of stars, and so on. And many other open packages are just vanilla. They don't necessarily provide all of the tools. We try to provide everything as run in our projects. And I said everything is open source, and we argue it's very scalable. And also this comes with a lot of test problems and examples that people can directly download and run. Hopefully, many of them are representative of the science cases people care about. So here's an example of a simulation. So it's a large-scale structure evolution. So what you have here is most of the gas in the main frame. In the bottom frame is just a dark matter in a small region, and you're studying the formation of a big cluster in this Flamingo simulation, which we run, which is actually the largest hydrodynamical simulation for cosmology ever run. So what you see here mostly is this white blob at the end is really the hot gas that's being ejected from the activity of the supermassive black holes and the evolution of galaxies in that dark matter halo. And why am I highlighting this? Because essentially the crux of the problem is that this can become very expensive to do because there's a lot of activity happening on small scales. You can see this box is very large, but the sort of the business end is only in a tiny region. Can we formalize this a bit more? He's just taking something from observations. So the top left would be some X-ray observation of a cluster. So that would be sort of this white blob I was showing that I was zooming in the previous video. So this is sort of the hot gas in a galaxy cluster. This is the Virgo cluster in this case. But what is generating this is really activity from AGN. And you can see a jet in the middle, but that jet is already 2,000 times smaller than the image on the left. And what is generating these radio jets in the center of galaxies? Well, it's mostly the supermassive black holes, and you here have the famous image of M87, which is another factor of almost 1 million smaller. So now you have sort of a correlation between what we're interested in is this really big white blob with really, really small time scales, right? So this very big challenge in terms of length scales that we need to solve. So we have a range of relevant length scales for our science, which is larger than 10 to the 10, range of time scales, maybe more than 10 to the 12, just take, length scales divided by speed of light or speed of sound. And the range of relevant density is 10 to the 20. And then on top of that, what is the challenge? Well, we're combining gravity with fluid dynamics, with magnetic field. And if you're brave, you can also add light propagation and charged plasma. And then on top of that, galaxy formation processes, right? So this is the ultimate challenge. So you could say, well, what if we just throw this, we have these exascale computers. What if I just make a really, really, really big grid, a uniform grid, and I'm going to throw all of this in a big exascale machine because, someone paid for them. We may as well use them. So let's take just a simple calculation. So I said we have 10 to the 10 range in length scale. So in a uniform grid, we have 10 to the 10 to the cube elements. Let's use a uniform time step because I'm lazy. So we have 10 to the 12 time steps. And then somehow I'm very, very good at coding. And I can do all of the operation in every resolution element in one floating point operation. So I have one flop per physics operation on the resolution element. And I divide all of this by an exaflop because I have exact access to an exaflop computer. If I do all of this, I still need 10 to the 24 seconds to finish my simulation, and which is 1 million times larger than the age of the actual universe. Right? So this is completely undoable, which means we need to have solution in software. Right? We need to have clever software that is not doing all of the work in a unigrid, in a uniform time step all the time. Otherwise, we'll just never get anywhere with the science we want to do. So what are the challenges? Well, we need to do this in sort of a multi-nested region. So we have gravity is complex because it has long-range forces, but also because gravity always collapses things. You end up with small regions where all of the action is, and a lot of boring universe where nothing happens, but still has to be in your computer. And then you have to use a local time stepping, meaning you can't just have a uniform time step everywhere, because otherwise you will be wasting loads of computation on regions where it's boring because of gravity again. And so you end up having time steps which are localized. You want to do more smaller time steps in region of interest. So now you're trading a lot of flop logic, a lot of operations, for a lot of thinking about where should the math be done. And then we are coupling hydrodynamics with your local forces. And then you also have all of this subgrid business, which adds a lot of terms which are not coming from PDEs. They're not coming from differential equations. And so they are really treated, and they can be annoying because they are introducing large jumps in fluid properties, for instance, which we have to tackle with your code has to be robust to these changes. And then because the universe is large and because we're interested in matching current surveys, we really need to have very large number of resolution elements. We're now doing a few times 10 to the 11 resolution element, but really we should be cranking up to like 10 to the 12 to the 13 resolution elements running for a month at a time on a computer. So very large memory footprint. So because we have these collapsing regions and because we have this localized time stepping, the load balancing and the domain decomposition are very hard. Right? It's not a static grid which just decomposes in chunks and every CPU has a fixed region of the grid. The domain decomposition changes over time and has to take into account the fact that some regions are more boring in terms of what happens in them than other regions where a lot of action is taking place, right? The region around a supermassive black hole will have a lot more time step, a lot more business going on than in an entire void outside of any galaxy. So just decomposing by volume, for instance, wouldn't work. So I mentioned we're using SPH. So this is smooth particle hydrodynamics, which means we're sampling the fluid using particles. Particles have a fixed mass, and then we define the density by having a weighted number of particles in a closed neighborhood, which means, and then the whole algorithm is that we're going to loop over the particles around, so they're essentially forming some sort of a stencil over which we can apply operators. So the particle loop over the neighbors to compute quantities via a weighting function. In a typical use case that you have 50 to 100 particles in the neighborhood, but they're completely disorganized, so they're not organized on a grid or something like that, which means that actually all kinds of GPU-friendly type algorithms are very painful to use because GPUs and all of these nice accelerators really like organized data, not completely disorganized data like this. So there are many SPH codes going back to the 90s or 80s, where it's like 3 SPH, but you probably heard of the gadget code, or maybe the gasoline code, the phantom codes, techniques used a lot, and many of them use an octree to find their neighbors, which is sort of nice because you anyway have an octree for the gravity, because we have all read Barnes Hut algorithm and read our textbook on how to solve gravity. So you already have an octree, and then you're going to reuse it for the hydrodynamics. Makes sense. It's easy, robust, and it's very parallelizable. However, what we do instead is that we decide we want to organize this chaos because we want to be targeting GPUs and other accelerator devices, which we're not doing yet, but still the spirit is there. So the idea is that what I can do is that I can also view my octree as being some sort of adaptive mesh refinement structure, and I can construct this grid until I have a certain number of particles per cell. And then because I'm looking for only 50 or 100 neighbors, naturally, my neighbors will be in the nearby cell. So if I took at the particle here in the green cell, all of its neighbors will be in the nearby cells. And once I have constructed all of my cells, I don't really have a chaotic behavior anymore. I can really just look for my neighboring cells around me and interact only with the neighboring cells, right? So that's already some sort of organization in this chaos. And then what is the key part here is that I don't have to predefine in which order I'm going to loop over all of my particles and all of my cells. All I require is that at the end of my time step, every pair has interacted. The order is irrelevant. And so what we really want to do is to really specify really small chunks of work. For instance, taking one cell and interacting all of the particles in, like in the pink cell here, or taking 2 neighboring cells, like the orange one, and interact all of the pairs in there, and then be the green one and so on. But I don't care in which order this is done, right? And why is this interesting? Is because different cells, because of gravity and because of this dynamic range, will have very different workload. So it's difficult for me ahead of time to tell you what is the best order to go over them, because I don't know. And I'd rather let the computer decide and make a whole list of all of the pairs to be done, and then the computer pull a pair, pull a cell, interact in them, and then put it back in the queue of operations to perform. And so that is really what task-based parallelism is about, that you try to reduce your problem in a set of small operations, then you put them in a list, and then you maybe have dependencies because maybe you want to time integrate after you compute the forces or something, but you have such an oriented graph of the operations that have to be performed, and then you let a runtime scheduler come in, pick a task, perform it, and then put the data back in memory, which has also loads of advantages because then the data you pull is really local to your thread, which means you don't have to worry about all kinds of MPI problems, all kinds of threading problems, and so on. So it also makes it sort of easier for people not familiar with HPC concepts to add their own flavor to the code or modify the equations, because there's no like complex HPC concepts at the heart of the calculation. And so you could also, and you can also represent your problem in an oriented graph. So for instance, you could say, first we need to move the particles, then we have a loop over the neighbors, this density loop, then we have a correction, and we have another force loop, and then we time integrate. And as I said before, all of the code within a task is very simple. No need for deep C knowledge. And so as a consequence, it's fairly easy to extend the code to change the equations in there. I don't have to worry about what an atomic operation is or a mutex operation is or any of this. My collaborators who don't necessarily work on the depth of the code can really easily extend the physics rapidly. Now, in real life, it's more complicated because you have more processes, you have gravity, you have hydrodynamics, you have star formation, so your oriented graph can become quite complex, but the spirit is there. The spirit of my advertisement trying to sell you task-based parallelism is still there. And what does it look like in action? Here's a plot you're probably not very familiar with. What you're showing here is work clock time on the x-axis, so it's you waiting in front of your computer for something to happen. And the 8 vertical bars are the 8 threads on your computer. And what I've done here, 8 cores, is I've colored what each core is doing by a different color. So let's say it's moving the particles would be this green, computing forces in orange, time integrating is in purple, and so on. I don't even remember what the key is here. But the point is that at every point in time, the different threads are doing different things. They just picked a different operation from the queue of operations to perform. But what is actually the most important here is that at the end of the day, when we reach the end of the step, they all finish at the same time. And that is interesting because it means we haven't lost any performance there's no wasted time. We don't have to wait for the smallest operation because there's always enough to do and enough to distribute over the CPUs. Of course, you want to go to a very big computer, so you need to worry about things like MPI. So you can do the same thing. You can just add send and receive operation as part of your task graph. It gets a bit more complicated, but this can be done. And then you can just execute. You can send the data while another core or while the same core is doing some operations. You can really hide the communications while you're running, and then once the data has arrived, you can unlock the next task and then continue walking through a task graph. But hopefully, if your domain are big enough, you have enough work to do locally while the data is being transported. Now, this is like way too much, but it's showing you that it works in action. Now, each of the 8 big blobs are, again, one of the plots I showed you before. And in each of them, I have 16 threads doing the same work. Not the same work, they're just local work, but it's the same spirit as before. And what you can see is that, again, within each node and within each thread, each core is doing something different at a given point in time. There's not like everybody doing an orange operation or a green operation. Maybe with a caveat that at the end, we all have to time integrate, so that always ends up at the end. But within each node, everybody finishes at the same time, and within each and all of the different nodes, which are the 8 main panels here, they all finish at the same time. So there's very little wasted time in practice. And this is very important here because, as I said before, it's very difficult for me to predict ahead of time where a black hole will form, or where a galaxy will form, or where a star will form. And so predicting ahead of time how to distribute the work is very difficult. I'd rather let the computer distribute the work on the fly by doing this scheduling of my mini tasks.
Matthieu, you should wrap up in the next.
Yeah, I'm wrapping up. And so we can show that this scales extremely well. So here's just an example of an actual real life calculation going from 1 node or going from 100 core to 60,000 cores, and we get only 20% weak scaling losses. This is just an example of showing simulations we have run in red compared to the literature in black. So you have compared to essentially all of the literature in black in terms of in sort of a simulation size on the x-axis, resolution on the y-axis plane, and we are running either larger simulation at fixed resolution than competition, or high resolution at fixed volume. So we are really pushing the boundaries of what can be run. And then finally, to complete my pitch on task-based parallelism, I argued it simplifies the domain decomposition thinking. It dynamically load balances. We can overlap the different parts of the physics, for instance, gravity, hydro, and maybe radiative transfer and galaxy formation processes. It provides a certain level of separation of concern. So users who are not familiar with HPC concepts don't have to worry about atomic operation, don't have to worry about MPI or threading. It's all inside the physics kernel. There's none of this. And in principle, you can port some of these sections to accelerators because you can just say, oh, only this section of the code needs to go on the accelerator. The rest can remain on the CPU. Now, if you were to transition your entire code, there are some caveats which are listed here on the right. Sometimes it's a bit niche. It's not always obvious how to couple with MPI. some newer frameworks like SQL and Cocos are maybe helping a bit with that. And actually it requires thinking in more code changes. It can just be like pragma openmp or numba something. It's not going to work. It requires really some deeper thinking about what needs to be done. I've shown you this slide before. It was my advertisement slide of what we have in the Swift code. I did my advertisement now of task grid parallelism in general as a concept. Maybe it's something you will be interested in looking into for your own application. I thought that would be interesting to discuss today. And I'll leave you with some pretty pictures of things we have run with the Swift code in general, going from galaxy formation, the interior of planets, clusters, some very simple hydrodynamic problems at the bottom, or some AGN jet activity in the middle at the bottom. And I thank you very much for your attention.
Wonderful, thank you. We can, if there's, I don't see any questions right now in the chat for that. I'm going to turn things over to Catherine in a second, but just one question, just to follow up what you were just saying. On one of your last slides, you mentioned transition to accelerators for some part. Has that started?
Yeah, so we are in the process. So we are moving some section of the solvers to GPUs. So the thing is, this is hundreds of thousands of well, more than 100,000 lines of code, and not all sections are interesting. Are not don't do a lot of heavy lifting in terms of the total runtime. So to us there is no real point in porting the whole code to GPU. And actually, probably only in terms of lines of code, maybe only a few % of the code need to be on a GPU. And so what we are doing now is porting some of the gravity operations, and in parallel to this, some of the SPH operations to the GPU. And then and that means we can keep the entirety of the MPI infrastructure and the entirety of all of the subgrid modeling and all of the operations untouched, meaning that people who are unfamiliar with GPU code don't have to worry when they edit some of these other sections. Okay. Having said that, the GPU code is not expecting incredible speedups that sometimes vendors advertise, but this is still to be seen. I think all of these particle-based techniques are very unfriendly to what we are being sold as devices.
I see. Okay. I know there is some particle stuff. There are PIC codes that make heavy use of GPUs.
That's right. Yeah, there are. But they are also based on very uniform grids in the background, so that helps a lot. And single time stepping is also friendly. But yeah, there is some inspiration we're taking from there as well, indeed.
Okay, great. I'm going to turn things over to Catherine. I think we have like 10 minutes, Catherine, but I'm sure we have some more questions.
Yeah, if anyone has questions, feel free to throw them either in the chat, or if you'd like to speak them, you can raise your hand or just unmute.
I keep seeing Josh's avatar, which has him with his hand raised in the avatar, which is very confusing. But
I'm surprised I haven't asked a question yet.
You have a question, or?
No, I'm surprised Josh hasn't asked a question yet.
I have a question, Catherine, if
yeah, please do, Michael.
I may. Devarshi, you mentioned that you are entering a sprint week, or you have 2 sprint weeks a year. Can you talk about the logistics of that, how that works? And it sounds like a neat idea.
Yeah, well, up until now, it was mostly just Amsterdam-based sprint week, because we only had Sebastian Guillot, who works in Toulouse in France. But now he has a bigger group in France, so we decided at least for spring we should go there. But essentially what we do is that we start planning maybe a couple of months ahead of time. We also have a Slack space, so that's where we start coordinating already. We create what's called a sprint board. So maybe I can quickly share my screen. Can show you from previous oops, yeah, is that, yeah. So projects, let me open all the closed ones. So we've already had a couple of sprints, as you can see, and basically we use like a Kanban system. We in here we already place any of the GitHub issues that have been previously raised, any new issues we want to work on, any kind of pull requests, they all go to do. And we always sort of, before, we sort of set a day. The first day we decide, okay, who's going to work on what, and we assign those tasks on the to-do. And we always assign an in-review as well. Like as I showed you earlier, that our main branch is sort of protected, that someone has to review before the pull request is merged. And then they, of course, once you finish it, you add it here. But when we do that, we sort of, maybe I need to open one of the closed issues here. Sure, we'll have a tag somewhere. So months ahead already, we start sort of tagging things that we want to address in this sort of sprint week. And then one of the things that we do is each day, like beforehand, we sort of try to organize who's going to do what. And then each day we have this, what's called a stand-up. This is something they do in industry as well during sprint weeks, is you discuss, you just discuss what you have been up to, what are you going to do today, do you need help, is there something that you need an expertise from someone else? So it becomes quite a nice and collaborative effort. It's something that you don't normally get to do in academia. You got kind of hunker down, sit in the same room, get a lot of snacks, get a lot of coffee, and just code all day.
And the people like really clear their calendars for this and the whole week?
Yes. Yeah. So again, this is like months ahead in preparation. So we set up a time when we are all free, which is difficult to find, of course.
Yeah, that's the trick.
Yes, indeed. But it is quite helpful, and it really helps you clean up your code base, improve it. Of course, we usually end up with more issues than we start with, because as we're following things, we come up with more ideas. But then we postpone it for the next sprint week.
Great.
I highly encourage any open source software developers with already a sizable team to organize the sprint weeks.
Great, thank you. Yeah, if there are any other questions, feel free to. Oh, yeah, do you have a question?
Yes, I have a question for Matthieu. So you showed that, that's very cute. You showed that within a single node, all of your core sort of ended up finishing at the same time. But when you were showing the different node graphs, it seemed like there were a lot of white spaces at the end. Was that like were the nodes just waiting for communication? Is that's just an MPI related thing, or?
Yeah, you spotted it. So the problem is that this is something we have been fighting for a long time. And the problem is that there's a difference between what an MPI library is supposed to be doing and what an MPI library actually does.
Right.
And so, there are some of these. So we are using asynchronous calls that are supposed to be asynchronous according to the standard, are supposed to be asynchronous according to the vendor, and then they're not always. And so the scheduler also, so then you end up with so-called progression issues where you send something to the MPI library, and then because suddenly the library you've given the hand to the library starts doing all the things in the background behind your back.
Right.
As the thread. And unknowingly, it's very unpredictable. So you can't say, oh, I'm just going to give you the hand now, you do your business, and then because I know how much time it will take, I can schedule around that. But there's no way of knowing how long that takes. And it's something which is a constant fight, and it's sort of library dependent, it's machine dependent. Anything on a cray will be terrible, typically. And it will really depend on the lower layers as well.
Right. I see.
So, yeah, good spot.
Anyone else? Alice?
No, I'm just wondering if I was going to ask a general question to the group. Are there talks that you would like to see us presenting, or themes that you'd like VAST to focus on in the next, few months? If you have ideas, please post them in the chat or speak out. Please, oh please.
And certainly we'd love to have more presentations from graduate students who just submitted their thesis. It's a great time to show off all the awesome work you did.
Yeah.
All right, I think we're good. We're basically out of time. We're still formulating what's happening over the summer, but we'll update our website and send out mailings as the schedule increases. And please do, continue to suggest talks, open a GitHub issue with talk suggestions if you'd like. And thank you, everyone.
Thank you. Thank you to our speakers. You both were fabulous.
Yes.
Yeah, it was very nice.
Excellent talks.
Thanks for having us.
Yes.
Yep.
Okay. Bye-bye.
Do we need to do any?
Let's stop the recording.
Oh, thank you.
Mm.